Hi, I'm Scott Resnik, and this is the intro to the Oculus Rift talk. I work at a startup that does contracting for AAA video games. I do mostly engine programming and optimizations for console games and things like that. So, but let's get into about the Oculus Rift. Let's just do a quick hardware overview. So. This is the headset, as you've probably seen it, and it has a single screen inside of it that has a resolution of 1920 by 1080, and it shares that screen between both eyes. So it has two lenses on each side, and they direct the image on the screen into your eye. The lenses let you focus on the screen that's up close, because normally if you didn't have a lens and you put your face that close to a screen, you wouldn't be able to focus on it. Your eyes wouldn't be able to. Also, inside of the headset, it has a gyroscope and a magnometer, which allows it to track your head rotation. And then in addition to that, it has an IR camera that you mount on top of your computer or around the side that detects IR LEDs, which are under the surface of the plastic on the actual headset, but you can see them in the image on the screen. You can see the little orange electrical bits going around. Those are all the IR LEDs. They blink at different rates, which lets it know which LED corresponds to which part of the headset, and then they do some tracking magic behind the scenes, and then you can tell where the head is positionally relative to the screen. So that lets your player look around and lean around, and then you'll be able to replicate that action inside the actual virtual world. So there's VR is rather new, so there's some best practices that they've kind of put out in the Oculus Connect talks that they did, which you can also watch on YouTube. But just kind of summarizing what they said really quick, everything looks the right size. So because you have two eyes, two cameras, and two images being streamed to both of your players' eyes, they get a stereoscopic vision. And as a result, they get depth perception. So everything in the world appears the correct size. So if you walk into a large building, it seems really huge, which is both good and terrifying, because you can walk into this like amazingly made level and you could look up and it'll feel gigantic and you'll feel like small and it'll be awesome. But it can also be terrifying, because you might be playing, say, Elite Dangerous, and you're flying in your little tiny spaceship and a much larger spaceship comes barreling towards you, and it's quite frightening. So the general gist right now is to be gentle with your players. Because if you aren't gentle, people who are new to the Oculus will have a very hard time playing it. So you kind of build up this immunity to the Rift when you start developing with it, because you're putting it on and you're seeing glitches in your level, and you're aware of it being a game, whereas someone who's new and putting it on, they're just experiencing like all of that all at the same time. So then things that jump out at them or collide with them or are massive and moving quickly can be kind of scary, and it's a problem. They can also experience vertigo. If you've played some of the games, there's some grappling hook type games, and you go jumping off a cliff, and then you'll be falling, and your body starts feeling like it's falling, and you can feel that in like the pit of your stomach. So don't try dumping your players off cliffs. It's not fun. Well, it's kind of fun, but take it as you will. Moving fast is scary, and above all else, never restrict their head movement, because if you prevent them from rotating their head, it starts to make them motion sick, is what happens. So they feel that they're moving their head, but what they're seeing in both their eyes isn't moving, and it creates this kind of disconnect between what they're feeling and what they're seeing. And it's like the same as when you're trying to read a book in a car, or if you're on a boat for the first time and you get seasick. It feels very much the same. You get like this awful feeling in your stomach. It's you shouldn't restrict the positional movement, but it's not as destructive to the player experience if you restrict the player movement. Yeah, it's just not recommended. And regarding movement, seeing things, seeing how things are moving and feeling how they're moving, the feeling that you're moving, I believe is called vection. And vection creates problems. So if you're creating a first-person game, like if you're playing like Team Fortress 2 or some other first-person shooter style game, you have your Oculus camera mounted on the player and they're running around. And they are seeing that they're moving through space, but they're sitting in a chair in their room or wherever they're playing, right? So their body isn't feeling that they're moving, but their eyes are receiving that they're moving, and it can make you a little bit sick. You kind of get used to it. They when the DK1 came out, they were calling it your VR legs, like your sea legs. It kind of goes away after a while, but it can be very daunting to a new person. That's why you see like funny YouTube videos of people like putting it on and standing up and then like walking around and then falling over in the real world. So as Oculus says, Oculus is a seated experience. So make sure your new players, anyone testing out, are actually in a chair, because it can go very bad very quick and they could break your priceless headset. The slide got a little screwed up, but I'll talk about the Unity integration because it's the easiest to use right now. There is a UE, an Unreal Engine 4 integration, which is also fairly easy to use, but most people are already playing around with Unity. So they changed the integration as of SDK version 4.3 or 0.4.3, I believe. And they made everything a lot simpler. So what you see is the view that you get inside your world browser thing in Unity is the OVR camera rig, which holds the center eye anchor, the left eye anchor, and the right eye anchor. And the camera rig's position in the world represents the default position. So when you start up with a game and you have the Oculus on, it sits in a position that's like 0, 0, 0. And any way they lean is offsetted from that. When they lean, it offsets the center eye anchor. And then when they rotate their head, it rotates the center eye anchor. So if you want to determine where one's looking, you use the center eye anchor. And if you want to determine where the reset position is, you use the OVR camera rig's positions. Some useful functions: they have the OVR manager .display.recenter pose. You want to expose this under some sort of key press, because especially if you're demoing it to a lot of people, like someone new will sit down and you'll put on the headset and they weren't in the same position as they were before. So their head will be off to the left, whereas the other player was right here, and then everything's a little bit wonky. So if you just have a key on the keyboard that you push and it assumes that where the person's head is, it recenters it. That's what that function does. And then you can get the look direction of where they're looking by using the center eye anchor .forward, so you can have your world react to what the player is looking at, which is like this kind of natural input that you didn't have before when you're playing with other games. You can so if they look over at an enemy or look at a UI panel in Elite Dangerous's case, the UIs will pop up as you look over in the appropriate direction, and it feels really cool. So take advantage of which direction the player is looking. So animation is hard. I wanted to dig into this for this talk because the last couple times I've been in a hackathon and tried to do something with the Oculus, we've had to skip over animation because things are difficult. You essentially need to end up using inverse kinematics, which essentially you have a bone chain and then you have a target position, and then you want to find out the rotations that the bone should have to match the location. And MechAnim, which comes with Unity, has this built in, but it's not great because the Oculus now has leaning support, right? So if you try to lean and you're trying to use the MechAnim's built-in inverse kinematic support to make the character lean, you find that MechAnim doesn't support that because you can only position the hands and the feet and give a look-at direction for the head. So it doesn't help you much if you want to have the player tilt their head. It doesn't help you much if you want to lean the body. So I thought this would be the most useful thing to dig into. So I ended up writing my own inverse kinematics, which is why it says stick it to the man, because we're going to use our own. Two-bone IK is pretty simple. It's easy to calculate, whereas if you add more bones into the bone chain, you get into weird numerical issues. There's two major algorithms, and they're all very complicated, and they take a lot of math, and it's not very fun. Thankfully, Ken Perlin, the guy who invented Perlin noise, he did a presentation at GDC a while ago. I forget the year, but he wrote out code in Java that solves a two-bone joint chain, which makes it easy to port. So I ported that for you. Two-bone IK is essentially what I said. You have some bones and you have a target position, and you want to make the bones move to the target position, which is simple when you have two bones, but you do run into this like case where there's an infinite number of solutions. So as you can see, like I have the two sides of that little diamond-shaped thing, and it could be anywhere on that oval, right? Because you can just swivel those two bones around and they meet the distance requirements. And it kind of looks like the little diamond marker from The Sims, except smoothed out. So you run into some issues. So Ken's method actually, it uses a point in the world to find the point on that oval that you just saw that's closest to it. So it resolves the infinite case into something that you can use. So the function I wrote for you guys looks like this. You take some bones, you get a start bone, you get an end bone, and an elbow bone. And then you get a target and a target rotation. So the target is the position you want to move, target rotation is what you want the end bones rotation to be, and then you get a blend weight. So if you wanted to make if you're trying to make the character's arm gradually outstretch, you'd calculate the final position, but then you gradually increase the blending factor so they move from whatever the position is to stretching out their arm. Super easy to use. And then there's also elbow pull point. Whereas, as I mentioned before, in Ken's solution, you can specify a point in the world that you want to use as the anchor for that oval solution. If you don't specify it, it uses the elbow bone's current position as that, so it'll pick the solution on that circle closest to where the elbow currently is. But if you want to specify a different point, which we do later in the talk, you can pass it in as an optional argument with that nullable vector3. The code will be up on my GitHub, github.com/LordTalks. It's not up yet, but I'll upload it as soon as I'm done with the talk. So what we're going to use the inverse kinematics for is matching the lean. So you want as the player leans around to be able to look down and see their character in the world, because it's a really cool experience. If you don't have like an actual model below the character, they don't feel like, you lose kind of your presence of the world. You feel like you're just floating there observing it. But if you look down and you see like a virtual body in the world, it kind of grounds you and it kind of makes you feel better. So what you want is for that body to react with how the player is moving through actual space with the headset on. So the head doesn't really matter because you can't see your own head unless there's a mirror, which just for our solution, just don't put a mirror in the level. But if you are doing that, you'll have to solve the last little bit of the head yourself. But the torso does matter because you can look down and see your torso, and you can like lean to the right and look down and you'll still see your torso. So you need your torso to move with your head. So that's the problem we're going to be solving. So first we need to get the bone chain. So in addition to my two-bone IK function that I wrote for you, I have a search children function because the built-in finding of children into Unity requires you to type out like a whole long path, and it's kind of annoying. And then also if you change models, so like if you're working with like a test model and then your friend's working with trying to get a new model rigged up, then you have to edit all those strings of those long paths. So what this simple ik.searchChildren does is just search for a child, matching the name, and then returns it. Super easy. And then you can use the bone chain by just accessing the parent, and then you get the whole chain all the way down, which is super useful. So then we're going to place an extra node in the world on our character, which I call the eye target. And the eye target is a game node that that you put in the center of your actual 3D character's eyes in the world. And we use this to help sync the Oculus's center eye anchor to the in-game center eye. And the reason we make it a game node is because it's much easier to place. Instead of like typing in values and then hoping that you get it in the right position, just make a game node, scroll it around in the world, and position it where you like. And then we'll store an offset from that eye target to the head bone, because we want to be able, because we're going to get the value from the center eye anchor. So we want to be able to go from the center eye anchor to where the head bone should be for the player leaning around. So we do the final minus initial. So the final is the eye target, and the initial is the head bone's transform, and then we get an offset. We're just going to store that for later use. After you get that offset, you can go ahead and collapse the player's head down with scale 0, because if your character is wearing glasses, or maybe they have some obscure geometry on their face, you'll see like certain polygons just pop up in the world. So the way you solve that is just set the scale down to 0, and it clumps down to being nothing, and it just gets the problems out of the way. But we have to set the local scale after you capture that eye target offset, because if you do it before, then the scale will affect the offset, and then you'll get an offset of 0, and it won't work, and it's no fun. So then we do the neck offset, which is the vector from the head bone to the neck bone, which we only use its length here, so I call it the comfortable neck length. And you're trying to find how long the virtual character's neck is, so that you can use that information to position where the actual neck should go when we do the IK to position the body. So we do the neck offset is equal to the eye target position minus the neck base's position, and the neck base is just the very bottom neck bone. It's like down here, and you can see it in the actual image there. I've drawn little debug lines, so you can see the white line is representing the vector. And then we store the comfortable neck length as its magnitude, and then I multiplied it by 0.75 because the strained, if you use the full neck length, and you were trying to do, like, say you're like trying to have that mirror in the level, or you're doing the multiplayer level, if you're storing that value as the full length, then you get these weird weird IK results because the neck is like the full length, and it's bad. So we just shrink that down a little bit, which causes the neck to kind of relax if you actually solve the IK on it. So then we're going to compute the target neck position. So what we're trying to figure out is from the eye center position of the actual in real world Oculus position, where to position the person's torso so that when they look down, everything looks right. So we're trying to position the neck where the real person's neck is in equivalent coordinate systems, because you have your world space world coordinate system and you have your in-game world coordinate system. So we compute the world target head pose, which is a mouthful, but it's the target position that we're trying to move the head to in world space, as the center eye, which is the Oculus's center eye anchor position, minus the center eye's rotation times the eye offset. So what that does is it takes that offset that we computed before, rotates it by however the orientation of the player's head, and then subtracts it. So this gets us to where the if the player's eyes are at center eye pose, where the head bone of the actual character should be. So then we've got that value. And then we want to compute the target neck pose. And the target neck pose is going to be based off of the head pose. So remember, we got that comfortable neck length, right? So what we try to do is we look at the line between where the resting neck position is, which I just call the bind pose's neck position, and where the target head position is. So you have a point in space. You can kind of see it on this gray line in the actual image on the thing, where the gray line, the end of the gray line, is the starting position for the neck, and then the line turns yellow, and then the ending position is where the target's neck, the estimated neck position is, or the head position. Sorry. So then we estimate where the neck should be by just following that line, the length of the comfortable neck length from where the head should be. So if we just say the neck is supposedly a straight line, which it won't be, but we just, for the sake of simpleness, call it a straight line towards where our neck's resting position is by the length of the comfortable neck, then we have to move the rest of the body to match up with that value. So that's what we compute the world target neck position to do. And then we take all that information and slam it into our two-bone IK, which it seems the slide has messed up on me, but hopefully you can see the code there. So we pass in the chest base, which is the very bottom node on the torso, which you can see in the white lines in the thing, where the white line starts. And then we have the chest, you can't read it, but it's like the chest middle, which is the bend in the white line on the image. And then we have the neck base, which is all the way at the top. And then we pass in the world target position and the center eye's rotation. So, the rotation doesn't really matter much because we're just swiveling a little nub of a neck, but we pass it in anyway. And then we also supply the thing I mentioned before, which is the elbow pull point, or in this case, we're pulling the back of it. So I noticed if you crouched with the Oculus, because it didn't have a good way of solving that little circle or oval issue, the side of the body would like slide out to the side. So he was kind of doing this awkward like little dance thing. So what I did was I just put another node, like I did the head targeting, the eye target node. I put one for the back and just dragged it out a little bit, and then called that the back pull point. So that always pulls that ambiguity towards the back. So if you scrunch down, his back crunches backwards, just like your normal back would, instead of to the side or forward, which looks even weirder. So that just helps solve a little bit of indiscrepancies with it. It's a fairly cheap operation, and the key thing that you want to keep in mind is to do it. There's different update functions. There's like update, and then there's fixed update, which you use for physics, and then there's one called late update. So if you're mixing these IK functions with Mechanim, which you'll probably be doing, so you can play like walking animations and running animations and hopefully like shooting or I don't know, climbing or whatever your game is about, they run before a function called late update. So if you put your IK call in the normal update function, it'll get overridden by Mechanim and you won't see anything. So you have to remember to put it in the late update function. So that way it overrides the values that you get out of Mechanim. And then if you put it all together and you put on the headset, you can look down and then you can see your feet and the body moving around. And then that should hopefully give your players a better experience when they're looking about the world so that they feel grounded instead of just kind of like a floating ghost in the world. It helps you like center. So like a common problem that you see with games that don't have any anchoring points is the player will gradually start to like rotate in their chair because they'll rotate their head and they start walking towards something and then they assume suddenly that where they've rotated is forwards. So then you'll get this like drift that the actual player starts doing, and they'll drift to the left or the right or something, and then they get all tangled up and it's no fun. So if you add actual anchoring points in the world, like a virtual body, they can look down and then they see that they're actually like off from where their virtual body is, and then they usually their brain will usually correct and they'll rotate back to center, which keeps them from drifting around in their chair, which is really annoying. Because if you're drifting and you're using a keyboard or maybe a joystick or something, your joysticks will get further off to the left, and it's an issue. So hopefully these functions help you deal with the troubles that you have in IK and animation.
Cool. A couple of questions. So the first one is for people who are interested in learning more behind your talk, what are some of the good resources places people can go to learn about Rift and all that?
Well, there's Oculus put on a conference called Oculus Connect, where they had a bunch of like the head people, like Lucky Palmer, the guy who started it, and Michael Abrash, who came over from Valve, and they all do talks, and they have them uploaded to YouTube. So if you just like go to YouTube and search Oculus Connect, you'll find a lot of information. And some of it's like technical, which you don't have to worry about if you're using Unity, like it handles all the integration issues, and some of it's technical, like if you want to learn about like time warp and all the things they're doing to make the correct frame rate happen, you can learn about that kind of cool stuff from the Oculus Connect talks.
Cool. And is Unity definitely the best place for people to start with Oculus development?
It's by far if you haven't done anything, it's by far the easiest because I didn't talk about it, but the SDK that you download from the developer.oculus.com, you can download, it actually has like a built-in player controller, and it gives you like a crosshair in the world, and it handles like the stereoscopic, and so you can just drop in this prefab, and then you can walk around the world in first person, and it handles all that for you, which is why I didn't talk about like movement and crosshairs and dealing with mouse input and stuff, because they handle it all for you. So it's definitely the easiest right now.
Are there any key differences between the DK1 and the DK2? Like, as a hacker who doesn't know anything, we're not looking at differences.
So the DK1 didn't have any positional tracking, and so that's where this camera thing came out. And at first, I thought the positional tracking wouldn't be really worth it because I was like, you're rotating your head, and it adds a lot of complications, which I just talked about with the IK. So I thought rotation would be enough, but then I started to actually play, like I played Elite Dangerous and some other demos with the positional, and it adds a lot more than you would originally intend. And then in addition to that, the screen got an up-res, like the DK1 only had 12, it was only 900 tall, I forget it's horizontal, but it had a huge what I called screen door effect, and it looked like had your face pressed up against the screen door, and it was very hard to see away. You still have some of that in the DK2, and then hopefully in the CD1 they'll get rid of that, but it is an issue. And they also upped the number of frames per second in the DK2 from 60 to 75. So, which also, like, if you're playing like a game at a computer, you think 60 frames is enough because it seems buttery smooth, compared to like movies and things. But once you put the headset on and start rotating your head, it becomes actually apparent that you need more than 60 frames per second. So 75 is what they have in the DK2. They're shooting for 90, for the CD1, but I'm guessing that's going to come down just due to hardware requirements. Like we don't have GPUs, things capable of outputting 2 eyes at 90 frames per second. It's too much of a technical challenge at the moment.
Sure. And speaking of like hardware requirements, like for people who want to get started with this, like what kind of computer they need to have, like what do they need to basically get started with the DK2?
Well, it depends on what kind of game you're building. If you're building larger games, you're definitely going to need a beefier computer, but you can get away in smaller environments like one room types of things with like a GTX 570 and up and whatever the mobile equivalent is. But if you're playing like I run a GTX 770 on Elite Dangerous and it struggles in parts, so you definitely need like 770, 780 Ti, or if you're lucky enough to have like a 970 or 980. Or whatever the rough equivalents of the AMD cards are. I haven't kept up with the AMD side, but you do need a beefy card if you want to be able to have larger experiences.
Totally. Closing thoughts you might have, and then where can people find you?
Well, you can find me on GitHub at github.com/LordTalks. It was in the talk. I'll scroll back to that if I need to. Some other closing thoughts, because Unity 4.6 came out, you got new UI elements. Those are also very handy because you can actually put UI like buttons and labels and stuff into the world, which makes it much easier to deal with on the Oculus. And then also the Oculus extension became available in Unity free, whereas before you needed Unity Pro, which was very, very pricey. Now everything I showed you today could be done in Unity free, so you can just download and play away with it.